Okie doke. About that time? Well, good afternoon, everybody. Hope everybody's doing well this afternoon, as well as you can. Under the circumstances, again, I feel like I should apologize every time. This isn't the best way to do a class, but we've got to do the best we can. So this is Psych 301, Research, Design, and Methodology. And so let's talk about a little bit about what's going to go down this week. First, very soon I'm going to send you an announcement about the stats quiz on Friday. So stats quiz 3 will be on Friday. And so the announcement will have the details about that. It'll include the last 3 stats tests, and we're going to learn the last stats test that's going to be on stats quiz 3 today. So there'll be 4 problems on stats quiz 3. It'll be like last time where you do the problems on your own paper, and then you email them probably to me, and then I'll grade them. Okay, so just like last time, and I'll announce the deadlines and the announcements and so forth. Okay, so more details about midterm number 3 stats quiz number 3 as we come up. Now I'm going to put up the flow chart for stats quiz number 3. You also have the directions for the test we're going to learn today. The test of independent frequencies is on the front page of the Canvas site. You're going to need the chi-square table that's on the front page of the Canvas site today as well. So today what we're going to talk about is our lecture is about non-parametric statistics. Non-parametric statistics is the title of the lecture today. Let me explain kind of what this is. I don't know if you know this or not. They have this psychology GRE, the psychology subject test. And if you're going to go to graduate school in psychology, lots of graduate schools require you to take the psychology subject test. It's really just a test to measure how much you know about psychology. And the way they decide what questions are going to be on the test is I'll get about every 2 years in the mail, because I'm the research methods instructor, Education Testing Services, which is the company that makes the GRE test. They will send me a survey, and they'll ask me which of the following topics do you cover in your research methods class. And they have a whole list of topics. Now, one of the things they always include on the list is, and they ask me about, is do you do anything about non-parametric statistics? I don't think this is a very important topic, but it is the kind of thing they would ask you about on the Psych GRE. And so I think you need to know what they are, and at least have heard of them, and be able to describe for somebody what they are. And so the goal of the lecture today is to tell you what these non-parametric statistics are, and then tell you enough information about them that you could probably answer the questions they would ask you on the Psych GRE about them. And then we'll actually do a non-parametric test in the second half of the lecture. Okay, so let me explain what these non-parametric tests are. So non-parametric statistics, that's our topic. And the thing is, all of the tests we've done so far, the t-tests and the f-tests, if you have to go look at the t-table or the f-table, you're doing what's called a parametric statistical test, a parametric statistical test, and that is a class of tests that require assumptions about the distribution of the dV, of the dependent variable, e.g. normality. That would normality. I did spell it right. Normality, in order to obtain correct p-values. Okay, parametric statistical test. Class of tests that require assumptions about the distribution of the dV, e.g., for example, normality, in order to obtain correct p-values. So you know when we go into the chart, the f-table and the t-table, we have the 0.05 values, the critical values there. And for those values in the chart to be statistically significant and alpha equals 0.05, they are making assumptions about how the dependent variable is distributed. The most important assumption is they're assuming the dependent variable is distributed normally. And you know that a lot of times it's not distributed normally. Very common, maybe even more common, for a variable to be positively or negatively skewed than it is for it to be distributed normally. Well, the consequence of that is that if you don't have a normal distribution of your dependent variable, well, what it means is that the p-values in the back are not going to be exactly accurate. That is, you won't actually be testing at alpha equals 0.05 if you use the numbers in the back, if you don't meet the assumptions. And so you might be testing at alpha equals 0.04 or 0.06 or something like that instead, because you haven't met the assumptions of the test. Now, in general, we do use these tests, these T and F tests, and the reason is that, in general, assumption violations are not of great concern because the tests are fairly accurate even when the assumptions are violated. General assumption violations are not of great concern because the tests are fairly accurate even when the assumptions are violated. So with real-world data, even if you don't have normally distributed dependent variable, it's not like you're going to be testing at some crazy alpha like alpha 0.07 or alpha 0.03. It's going to be right around 0.05, but it's not going to be exactly 0.05. That is true. And so this really, really bothers some statisticians that we go around saying that we're testing at alpha equals 0.05, when in fact we're not meeting the assumptions of the test. And so what they have done is there are some statisticians who have developed tests that don't have these assumptions. So let's talk about these tests. These are called non-parametric statistical tests. Non-parametric statistical tests. And this is a class of tests that do not assume the DV is normally distributed. A class of tests that do not assume the DV is normally distributed. In other words, they have less restrictive assumptions than the parametric statistical tests that we've been running. And so it sounds like it's better. Hey, we ought to be doing these tests. They don't have this assumption that's often violated. Well, if that were the case, if they really didn't make any assumptions at all about how the dependent variable is distributed, I think people would use these tests more. But the problem is almost all of these non-parametric tests, they actually do have assumptions of their own. Specifically, they generally assume that if the dependent variable isn't normally distributed, at least it's symmetrically distributed. Let me show you what I mean by, here's an example of a symmetrical distribution. That's not a normal distribution. You may be aware your computer has a random number generator in it, and it will generate a function that generates a number between 0 and 1. And so if we were to plot the frequency distribution for the random number generator on your computer, we would not get a normal distribution. We get this rectangular distribution. Essentially, any number between 0 and 1 is equally likely for your computer to spit out. So if we were to plot a frequency distribution graph like this for the random number generator on your computer, we get this rectangular distribution. Well, this distribution is symmetrical. That is, if we fold it in half, it would be the same on either side, and so it meets the assumptions of being symmetrical. But you can see it's not a bell-shaped curve like a normal distribution, so it's symmetrical but not normal. And so the non-parametric tests that we're going to talk about, the assumptions are met for a distribution like this. But the problem is I don't know any real-world data that actually looks like this, or it's hard for me to come up with a variable. In fact, I cannot come up with a variable that is symmetrically distributed but not normally distributed. Here's what usually happens when we're violating an assumption. We got like the positively skewed distribution here with this long tail, and you can see this distribution is definitely not symmetrical. It's not the same on the left and the right sides here. If we folded it in half, it wouldn't be the same. So that's why I think one of the main reasons I think why people aren't a big fan of these non-parametric tests. We'll see other reasons they're not fans too. But the idea is that you're going to violate their assumptions too, and so why not go with the parametric statistical test if the assumptions are going to be violated anyway? Well, let's talk about some of the advantages and disadvantages of these types of tests. So advantages of non-parametric tests. Advantages of non-parametric tests. First advantage is that they have less restrictive assumptions. We already talked about that. They don't assume that the dependent variable is normally distributed. Most of them do assume that it is symmetrically distributed. But certainly they don't have as many assumptions built into the p-values as the parametric tests do. And then another advantage is they're often easier to calculate than parametric statistics. If you remember that between subjects t-test, for example, you have to test, if you're doing the parametric test, you got to test whether the variances are different to determine the version, and then you have to do the version. It's a very long test. But the equivalent for the non-parametric statistics is much, much faster to do. So those are the good things about non-parametric tests. Advantages of non-parametric tests. Okay, a couple disadvantages. One, and this is one of the big ones, tend to be overly conservative. All right. Liberal test is a test that finds lots and lots of reliable differences in your data. A conservative test is one that's hard, means it's hard to find a reliable difference in your data. And so if you use a non-parametric test, you're a lot less likely to find an effect of the IV on the DV than if you use the parametric test that we've been using. That's why psychologists don't like them. It's because you can get all the way done with your experiment, use the non-parametric test, and you find the IV didn't affect the DV, when if you had used the parametric test, you might have found that it did. And so they tend to be underpowered. That is, a lot more likely to make a type 2 error with the non-parametric test than you are with the parametric test. And then the second one, and this is a fatal one in some cases, is that no non-parametric tests exist for some research designs, e.g. the big one is factorial designs. Okay, so there isn't a non-parametric equivalent test for like the between subjects factorial ANOVA, or in general we learned just the between subjects factorial ANOVA, but you can do factorial within subjects factorial ANOVAs, or even mixed where you got between and within, and those are by far the most common sorts of experiments that psychologists do. And so if you've done a factorial experiment, you have no choice except to use the parametric test that we've been learning. And so I think that may be, above all, the reason why psychologists use them is usually they're doing factorial experiments, and if you're doing a factorial experiment, the parametric test is that F test is the only one you really have at your disposal. Okay, so I think that's most of what you should know about this. Now, maybe, most psychologists do not use these tests, but you may have a psychologist that does. And so what I'm going to do is I'm going to make a little table. I'm going to put the parametric test over here. I'm going to put the non-parametric, please, metric test over here. So this is going to be, for the tests we learned, there's the parametric test that we learned, like test of a single sample mean. I'm going to have trouble putting these in. Okay, that was a t-test, remember. Well, there is a non-parametric equivalent. It's called Wilcoxon's assigned ranks test. This is going to get a little ugly, but we'll get it done. Okay, that's Wilcoxon's signed rank test is the non-parametric equivalent. So this is, I'm going to give you these tests. You don't have to memorize these. I won't ask you on the exam. But I wanted you to know if you see an article where you think, for example, it should be the between subjects t-test. That's the next one we're going to do. But in fact, they did Wilcoxon's, this is called the rank sum test. Okay, the rank sum test. Well, they did the right test. They were just doing a non-parametric equivalent of the parametric test that we learned. For the within subjects t-test, the non-parametric equivalent is called Fisher's sign test. For the between subjects one-way ANOVA, the equivalent is called the Kruskal-Wallis H test. And then last one, the within subjects one-way ANOVA, the equivalent for that is Friedman's chi-square R test is what it's called. Friedman's chi-square R test. That's the equivalent of the within subjects one-way ANOVA. Okay, so I just wanted you to know the names of the equivalent tests here and have them in your notes. If your professor that you're working for in graduate school wants you to do the Wilcoxon's rank sum test, I'm going to give you, instead of the between subjects t-test, I'm going to give you a little reference of a book that can tell you how to do all these tests. So this is Weick, E.L., 1985, numbers, a primer of data analysis. That's published in Columbus by Merrill. And that's a really good book that shows you how to do all of these tests up here if you need to do one. But I'm betting you won't. So here's the thing. Here's kind of my take-home message from all of this. Take-home message. And that is most psychologists prefer parametric tests because of their greater power and because they can analyze factorial designs. Okay, so that's why 95% chance if you go to graduate school, you'll never have to do one of these non-parametric tests. But there are a few psychologists who do like to use these, and so I wanted you to know what they were, and now you should be able to answer all the questions on the Psych GRE. All right, now for the next section, the TA has posted a video of how to do the next test, and the next test is the test of independent frequencies. That's also called the chi-square test. The chi-square test. Now, I usually will call it the chi-square test. I don't think you'll actually hear a real psychologist call this the test of independent frequencies. Usually you call it the chi-square test. Okay, now, here's the weird thing about this. This is a new thing that we're going to analyze. So we've learned a bunch of tests for analyzing means, right? Like the ANOVAs, between subjects t-test, within subjects t-test, and test of a single sample mean. Those are all tests of means. And we've had tests of variances. We had the between subjects variance test and within subjects variance test. We had a test of relationships. That's correlation. Correlation is test of relationships. And now this is the last thing. This is a new type of data. This is frequencies. And what this means is, I should say, if you're going to not go into psychology, but going to do research, say, for a business, this is the most common type of test you would use, because this is going to be a test you would use to analyze the results of survey data. So if you were, I don't know, had two ads and you wanted to see which one people like better, so they got to vote for which of the two ads they like better, and one ad got 312 votes and another ad got 290 votes. Well, is that a statistically reliable difference in the number of votes that each received? That's what we do when we test frequencies. If I wanted to know, for example, if the number of Democrats, Republicans, and Independents in Story County was reliably different, that would be the test of independent frequencies. I get a count of the number of Republicans, the number of Democrats, and the number of Independents, and then I would do this test of independent frequencies, the chi-square test, to see if they're different. So we're not comparing means, right? Means is when you add up the scores and divide by the number of scores. We're comparing whether the number of votes one thing got differed reliably from the number of votes another thing got. Now, this test requires you to use a new table, and the new table is on the front page of the Canvas site. And it's the chi-square table. So it's the chi-square test. Chi-square table is what you need. And I want to show you something about it. Here's the T table, and this is going to be true of the F table too. I don't know if this is big enough for you to see, but here's the 0.05 column. It's in bigger type. But if you'll notice, as the degrees of freedom go up on the T table, the critical values go down. So bigger degrees of freedom leads to a smaller critical value in the T table. Here's the F table, which you almost certainly can't see, but it's the same relationship. As your degrees of freedom go up, the critical value goes down. That's true with both T and F. But here's the chi-square table that you're going to be using today. And the chi-square table, I'll make it a little bit bigger. Okay, here's the chi-square table. What you can see is as the degrees of freedom for this one go up, the critical value goes up as well. And that's right. That's the way the test of independent frequencies works. Now, I'm going to give you both the 0.05 and 0.01 values here, but for our class, you're always going to be using the alpha equals 0.05 column. So now what you want to do is we're going to stop this video, and you should go do the video on the test of independent frequencies. The TA is going to be doing problem 60, the very last problem in the book, problem 60. So I'd recommend you get out your stats calculators and work the problem along with it. Okay, I'll have another lecture up for Wednesday, and then I'm also going to post the information about the stats quiz in the announcements section. So I'll see you again on, talk to you again, so I won't see you on Wednesday. Bye-bye.